Hey dudes, Dude the Builder here, and in this episode of Zig in Depth, we're going to be talking about the ArrayList in Zig. The ArrayList is a data structure found in the standard library, and it pretty much provides the functionality much like an array, but since arrays have a fixed size that can't change, the ArrayList gives you the opportunity to grow or shrink the ArrayList as necessary during your program execution. So in that aspect, it's a bit more flexible than a normal array. But like an array, all the items of an array list have to be of the same type. And for those coming from languages like Java, there is an array list there, and Rust and C++ have the vector, which pretty much provide the same functionality as the array list in Zig. And since we are going to be making some room for a data structure that can grow, we're going to need an allocator. And in this case, we're going to be using the general purpose allocator, creating here an instance with this variable GPA. And we are using defer here to call the dinit on that general purpose allocator to free the resources once we finish execution. And here we see an example of how to create an array list with the init method and passing in the instance of the allocator, in this case from our GPA. And you can see that ArrayList is one of these generic functions that takes a type. And in this case, the type is going to be the type of the items of the array list, okay? And this init method basically creates an empty array list. As we see here in this comment, the length is going to be 0 and the capacity is going to be 0. And these concepts are important in case of an array list because the length is the actual number of items that have been added to the list, whereas the capacity is the allocated space that has been set aside with the allocator that we passed in. And the capacity and the length not necessarily have to be the same, but always the capacity is going to be greater than or equal to the length, okay? If we're going to add items to a list, in the case where there is enough capacity to hold those new items, then no new allocation is going to happen. But if there isn't enough capacity, then a new allocation has to be made, and the existing items would have to be copied over, and the pointers, if you have any pointers to the items directly in the array list, then those pointers would be invalidated, okay? So it's an important detail to have in mind. Here, once again, we're using defer to call the init. Anytime that we have a structure that needs to clean up, we will see this convention of the init method. And we're using defer to defer that execution until the main function exits, okay? Here, we're going to see an example of how to add items, with basically the most fundamental operation that you can do on an array list is add items to it. And we use the append method, which can fail. This is why we're using try here. And it can fail because it possibly may need to allocate, and memory allocation may fail. This is different from other languages where you have these types of data structures, and when you try to add an item and there isn't enough memory, the program usually just crashes, okay? In Zig, you have an error that's returned in that situation, and you can handle that error as you see fit, okay? And here, I'm using a little function that I wrote that's called print list to print out that list. If we move down here to the bottom of the file, we're going to see here this function takes in on a stud array list of U8. We're being specific here to our examples. And we are simply printing out this list prefix. Then we iterate over the items. This is how you can iterate over the items of an array list. It has an items field, which is basically a slice of the items that have been added to the list. Once again, you see the simplicity here in Zig. where the array list is basically a wrapper around this slice of items, and it provides a lot of useful functionality. But if you need to interact with that slice, you can. Like we're doing here, we're iterating using a normal for loop, and we're printing out those items, and then we print out a couple of new lines. Okay. So going back here, we're going to see next up that you can use an array list as a stack. And this is really useful. You don't need another separate data structure in the standard library to have a stack in Zig. You can use the array list. And the only difference from the conventional stack naming conventions is that instead of push, we're going to be using that append method that we saw earlier. This adds an item to the end of the list, or if you're looking at it from the stack perspective, it adds an item to the top of the stack. Here we add that new line and we print the list. Then we call pop. In this case, it does use the normal name that's usually used in stack nomenclature. And when we pop, we remove the last item from the list, or as you might see it in the perspective of a stack, the item that's at the top of the stack. Okay, and it returns that item, which we're ignoring here, and then we print the list once again. So let's look at the output so far. Here we have that first print list once we created and added the hello world characters. Here, as you can see, this printout has an extra new line here, which is the new line that we got from calling append. And then that extra new line is gone the next time that we print, which is what happened when we did the pop. Okay, so the new line is gone. Okay. Now, let's go back here to the code. In the specific case, as we're doing here, that's why I created this as an array list of bytes of U8. When it's an array list of bytes, you can use the array list as a writer, which means that you can use the methods of the write interface in Zig. Like print, for example. Here we obtain the writer by calling the writer method on the list. And then we can call any of the methods that the writer interface in Zig. Print is one of them. And we can use all of the functionality of formatted printing, as we saw in the earlier video. Here we're just printing out this 42. But we can then use an array list as a writer, which can come in really handy in situations, for example, when you're reading bytes from the network or reading from a file. You want to save them to an array list, you can treat the list as another writer and just do copies from one reader to that writer. Okay. There's also a handy little method called pop or null. Pop, if the list is empty, pop will generate an error. Not exactly an error. It'll basically panic because it asserts that the list isn't empty. But if you simply want the option to iterate over the list until it's empty without panicking, then you can use pop or null, and given the modality of the while loop with an optional, pop or null returns an optional item. So when it reaches the end and the list is empty, it's going to return null, and we're going to exit this while loop. Okay, so here we're iterating using that list as basically an iterator, and printing out the specific items, calling pop or null. But this time, this would be a consuming iterator because we're popping, so we are removing these items from the list. Okay, and then we add a couple of new lines, and then we print the list once again. So if we see here in the output, we're going to see that we have the contents of the list here being printed out in reverse order. That's an important detail to note. When you're doing pop, as is the normal stack behavior, you're popping from the end or the top of the stack, and you're going to have the items, the last item that you pushed in or appended is going to be the one that's going to come out. So basically the order is going to be reversed. Okay, and that's what we have here. And then after that, we try to print the list, but the list is empty. Okay, so this is why we get no output here in this line. So next up, we have here the append slice method, which you can use to append a slice of items all at once. In this case, since we have an array list of bytes, we can append this string literal, which will be coerced to a slice of bytes. Okay. But for example, if you have an array list of structs and that you defined, and you have a slice of your structs that you obtained from another source, you can use append slice to append them all at once. Okay. Next up, we're going to see how you can remove an item at a specific index from the list. Here we added the hello world, and at index 5 we have this comma. So here we're doing ordered remove 5, so the comma should be removed. And this operation basically removes the item at that index, and then it shifts the remaining items over to fill up that slot that's opened up. So let's look at that output. Here, as you can see, we have the hello world with the comma, and here the comma is gone. Okay. So it's important to note that, as it says here in the comment, this is an operation that can be quite expensive if the list has many items. Its complexity is O(n). So this means that its complexity will increase with the length of the list. And this is because it has to shift over the remaining items. And for example, in the worst case, if we are removing the first one, then all of the items have to be shifted over. They have to be copied over. Okay. So it's important to have that in mind. But there is an option if you don't care about the order of the list. You can use this method, which is called swap remove. And swap remove, what it does is it will remove the item at the index that you're specifying, and it will then fill that slot with the last item. So it'll move the last item to that slot that just opened up. And in that case, then the other items don't have to be shifted over. So this operation is O(1). Okay, it's a lot more efficient in that respect. So let's take a look here. And you can see that here, that we have the hello world here, okay? And then we called that swap remove, and what it did, it took the exclamation point and put it in the slot of the 5th index, which was the item that we were removing, okay? And as I said, the array list is just a handy wrapper around a slice of items. It provides a whole lot of functionality. I'm going to put a link in the description to the source code in the standard library. Aside from seeing all the methods that are available, that ArrayList source code is really, really well written, really well documented, and it's a great tool for learning how to do things in Zig, especially handling memory allocation. So here we see that we can access directly that items slice, okay? And we are assigning a value here. We are assigning the space here. This would be, this literal here will be coerced into a U8. And then we print that list. So here we had the exclamation point in that position, and now here we have the space. So in effect, we can manipulate that slice of items directly, okay? If you have a situation where you need to detach that slice of items from the list, and at the same time you clear the list or reset it to be empty, there's a method for that. It's called toOwnSlice. Okay, list.toOwnSlice here is going to return the slice of items, and basically it's going to reset this list to the empty list, just like when we created it initially. But what does that mean? It means that now we have to take care of freeing this slice of bytes, okay? It's not going to happen when the dinit method on the list is called, because we are passing ownership here of that slice of bytes. So you can see here, this is what we have to do. We're calling here defer for the allocator to free those bytes, okay? And then we print the list once more, which here we see, once again, we have the empty list, okay, after toOwnSlice. Now, we're going to see that if you have the situation where you do know the initial capacity that you're going to need, you can make your program a little more efficient by using this version of the init method. It would be init capacity. And this takes the allocator and the capacity that you want to set aside, allocating initially for this array list. And because of that, init capacity can fail because it's going to be allocating. Init doesn't fail because it doesn't allocate anything. It's just an empty list. But init capacity can fail because it does allocate. So that's why we're using try here. And once you use init capacity, you can, as I said, have a more efficient execution when you're appending, because you know you have the available capacity. Then you can use this method, this version of append, which is append assume capacity. Okay, so in this version, the method can assume that the capacity is going to be available, and it doesn't have to try to do any allocation when trying to append an item to the list, okay, which can be more efficient. And here we print out the length and the capacity, and then we print out the list. So let's look at that in the output. And here we go. We have the length is 5 because we added hello, and the capacity is 12 because that's what we set aside when we called the init capacity method. Okay. And here we're going to see an example of a function that uses an array list internally for its convenience in terms of gathering bytes or any type of item that you want to gather up. The array list can be really handy, and you can use it internally in a function, and from the outside interface of the function, you don't have to know that you're using an array list. You just pass in an allocator, as we're doing here. And we're passing in this string literal, which would be like a slice of bytes, would be coerced to that. And here, once we obtain that result, which is going to be a slice of bytes, we're calling defer here to free those bytes, and then we print them out. Okay, and this is here, the output that we're seeing here. Let's take a look at that function. Here it is. It's gather bytes, takes an allocator, it takes a slice, which is a slice of const u8. And since we're going to be allocating, you can see here we're going to be using the error union here with basically the inferred error set. And we're going to be returning a slice of u8, okay? Which means that you can modify these bytes that are returned, and you have to free them once you're finished working with them. And what we do inside the function is we create a list here, and we can use init capacity because we know that we basically are going to be copying this slice. So we have the length of that slice, and that's what we're going to use for our initial capacity. That space is going to be allocated right there on the spot. Here we have defer to list.dinit because we're not going to be using this list outside of this function. This is only for internal use only. Here, then, we iterate over the bytes of the slice, and we use, once again, append assume capacity. We add those bytes to the list, and we return the result of toOwnSlice, which will basically move that slice outside of the list, the ownership, and that's what's going to be returned. And the list will be then empty. So when this the init is called, the list will already be cleared and empty. So in theory, you really you could omit this, but best practice dictates that you should always do a dinit because you don't know what may happen in the future, and it doesn't really hurt. So with that, that's basically the fundamental operations available on an array list. There are other methods that allow more advanced uses. Manipulation of the internal memory of the array list that are available, and you can see those in the source code. I'll put the link in the description. But the array list is really useful data structure available in the Zig standard library, and I hope you can make the most of it. So do the builder here. I'll see you in the next one.